Surface flow refers to the movement of fluid over surface. It's typically used in a context of natural system, such as the flow of water over land or structure, but it can also refer to the flow of any fluid over a boundary in engineered system. Surface flow visualization techniques are used to analyze the flow of fluid over surface, often providing insight into flow pattern, turbulence, and interaction with boundaries. Oil flow visualization. A thin layer of oil mixed with a dye or pigment is applied to the surface. As a fluid, in example given, air or water, flows over the surface, the oil streak form pattern that reveals the flow direction and intensity. Here are the example. Formula to compute the oil flow velocity. To compute the surface shear stress is by observing the velocity of oil streak. The velocity of oil on the surface is proportional to the shear stress acting on the surface, as oil flow is driven by this stress. This is the formula. Tau, or the wall stress, is equals to the mu dynamic velocity of the oil times the changes in velocity of the oil over the changes in distance. The second one is the empirical relationship for wall shear stress. Oil flow velocity is hard to measure directly, so empirical relationships are used based on the streak length or streak thickness. An approximation for the wall shear stress from oil flow pattern can be derived using an empirical relationship. The formula for empirical relationship is tau wall shear stress is equals to the dynamic viscosity of the oil times distance over time. The third one is skin friction coefficient from wall shear stress. Once you have an estimated of wall shear stress, the tau wall shear stress, you can compute the skin friction coefficient, which is an important non-dimensional parameter in aerodynamic and fluid mechanics. Skin friction coefficient is equals to tau, or the wall stress, over fluid density times free stream velocity. To simplify, skin friction coefficient is equals to tau shear stress over dynamic pressure. For example, we have dynamic viscosity of oil, which is 0.05 Pascal second, and the length of oil streak, which is 0.1 meter. For our time, we have 100 seconds, and free stream velocity of 50 meter per second, and the density of fluid, air, 1.225 kilogram meter cubic. So we have the given dynamic viscosity of oil, which is 0.05 Pascal second, length of oil streak, which is 0.1 meter. We have time 100 seconds and free stream velocity of 50 meter per second, and the density of fluid air, which is 1.225 kilogram meter per cubic. Using the empirical relationship for wall shear stress from oil flow streak length, we compute the wall shear stress. So first we have the formula, which is tau wall shear stress is equals to mu oil viscosity times distance over time. So now we will substitute our given, which is for our mu oil viscosity, which is 0.05 Pascal second, for our distance 0.1 meter, and for our time, which is 100 seconds. And we will get the answer 5 times 10 raised to negative 5 Pascal. After we get the empirical relationship of tau of wall shear stress, so now we can compute the skin friction coefficient. Skin friction is equals to 2 times tau wall stress over dynamic pressure. So now let's substitute our given. 2 times 5 times 10 raised to negative 5 over 1.225 times 50 squared. So first we will calculate our denominator. So before that, we need to calculate the 50 squared, which has a exponent of 2. It will be 2,500. So now we can calculate our denominator. 1.225 times 2,500 is equals to 3,062.5. So now we will compute the skin friction coefficient. So 2 times 5 times 10 raised to negative 5 is 10 times 10 raised to negative 5 over our denominator, which is 3062.5. So we will have the answer 3.27 times 10 raised to negative 8. So this is the interpretation of our answer. For our step 1, the wall shear stress, which is 5 times 10 raised to negative 5 Pascal, so which is relatively small, indicating that the shear force acting on the surface are low. So for our second step, the skin friction coefficient, so the skin friction coefficient is 3.27 times 10 raised to negative 8, suggests that the drag due to the friction is minimal at the location on the wings.
The wing's shape creates high velocity, low pressure, and low temperature air on the upper surface. Water in the air condenses in the colder temperature, and we get to see the regions of lower pressure. It's the difference between pressures on the upper and lower surface of the wings that generate lift. At the wingtips, we see the lift production decreases in part by design and in part by lower surface, high pressure, air leaking, to the lower pressure upper wing surface. Here's a picture of a paper airplane in a small smoke tunnel. You can see the smoke swirl as it passes the leading edge of the wing on the far side of the tunnel. You can watch a movie of this experiment which shows the motion of the smoke over the wing. Thanks to Dwayne Hunt for the production of the movie clip. Tufts are another old visualization technique that is used in both flight tests and wind tunnel testing. Tufts are small lengths of string that are frayed on the ends. Popular materials for tufts include monofilament nylon and polyester or cotton. Number 60 sewing threads. Tufts may be coated with fluorescent dyes to increase visibility for photography. Smoke is used to visualize the flow that is away from the surface of the model. Smoke can be used to detect vortices and regions of the separated flow. Tufts align with the direction of the airflow. You can calculate the angle of the airflow, theta relative to a reference direction like the surface or body axis by using trigonometry based on flow velocity components. Theta is equals to the arctangent of Vy divided by Vx.